Hello. So in this example, we are computing an indefinite integral, right? So remember, indefinite integrals are sort of this notation, this way of sort of capturing all of the antiderivatives, right? So really sort of what I want to do when I'm doing an indefinite integral is to sort of find the antiderivative for the integrand, for the piece, inside in here. And then make sure that I sort of capture all the other ones by using that plus c thing, right? So remember, I can split up the process of finding that antiderivative by term, right? So I can look at this thing and say, okay, I don't necessarily want to tackle all of this at once. So I'm going to break this up by looking at the integral of 1 over x dx minus the integral of 2 to the x dx minus the integral of x cubed dx. Oh, I don't know where that 3 came from. My brain is on autopilot to somewhere. Who knows? Try that again. dx. Okay. So going through these sort of piece by piece, I want a thing, right? I want an antiderivative. I want a function such that when I take the derivative of that function, I get 1 over x. But remember, this is sort of exactly what the natural log is. So really, I sort of immediately can do this one by just remembering that the derivative of natural log, right? So as sort of an aside over here, if I took the derivative d dx of natural log of x, this is 1 over x, right? There's a small hiccup here that there's no sort of inherent domain restriction. So here, right, the x can only be non-negative, can only be strictly positive, can't be 0 either. Here, x could be positive or negative. So I have to sort of account for that by remembering that this is the natural log of x, but not just the natural log of x, the natural log of the absolute value of x, right? And notice here, I'm not going to say these are equal because it's a little dodgy to do that because I'm not putting the plus c here. I'm going to do that at the end. I'm just doing sort of each piece on its own, sort of in scratch work, I guess you might say, sort of in my head or sort of off to the side. Okay. Now, I'm going to skip to the end one here. So I want a function such that the derivative of that function is x cubed. Now, I might just remember, right, my core function integrals, but if you don't, remember that sort of taking a derivative of a polynomial, right, if I were taking a derivative of something like x cubed, it would lower the power by 1. So whatever this thing came from, it needed to have 1 higher of a power, right? So I might start with that and be like, okay, it should be something like x to the 4th. I don't think it actually is x to the 4th because that would be way too easy, but I think it's something close to that. So then I take x to the 4th, take the derivative, and see what I get, because the idea is I want something whose derivative is x cubed. Well, if I did that, then I'd have to pull down the power and subtract 1 from the power afterward, and this would get me 4x cubed, which is close, right? That's almost what I want. I want x cubed, not 4x cubed. So instead of taking the derivative of this, I could try taking the derivative of 1/4 of that to sort of undo that 4, right? So 1/4 x to the 4th. Well, the 1/4, this is why it's nice that it's a constant, right? The 1/4 comes out. So it's really 1/4 times 4x to the 4 minus 1, and that becomes just x cubed. So this tells me then that my actual antiderivative for the x cubed is 1/4 x to the 4th, right? And similarly, I'm going to do the same sort of approach for this last one, this 2 to the x, where again, if I don't remember my core rule, my core function rules, I'd be like, okay, well, exponentials, right? They're the special functions. They sort of stay themselves almost, right? So you might think, okay, if 2 to the x came from something, it probably came from 2 to the x of some form, right? Because they don't actually really change much, right? There's a little bit of an asterisk there. But again, same idea. I'm gonna do the same process where I'm like, okay, well, let's start by seeing what happens if I take the derivative of what I think is the answer, right? So I don't, again, just like here, like I don't really think 2 to the x is the answer because that would be too easy. But you know, maybe it should be sort of in the same vein. I might be able to manipulate it to make it into the right answer. So derivative of the exponential, right? Remember that's going to be, so again, if you don't remember how the exponentials work, right? E to the x is the really special ones. You do some sort of like natural log e to the whatever and do shenanigans. Chain rule involved, but we'll assume or hope that you remember the rule for this part at least, which is that I'm going to have the natural log of 2 times 2 to the x, which again is almost what we want, but not quite, right? We're off by, again, a constant, this natural log of 2. So I'm going to check what happens if I just sort of divide out by that beforehand. 1 over natural log of 2, 2 to the x. Well, again, nice thing about it being constant is I don't have a product rule or anything going on, right? This just comes out, so I have 1 over natural log of 2 times, but then I end up with this thing, natural log of 2 times 2 to the x. Those cancel, and I do indeed get 2 to the x. So that tells me that this really is the antiderivative, this 1 over natural log of 2 times 2 to the x. Okay. So this tells me then that my overall full antiderivative is going to be putting these things together. So that would be the antiderivative, but I want the indefinite integral. I want all the antiderivatives, right? Everything that's possible, but I don't know that initial starting condition, so I need that plus c. So I'm going to have the natural log of absolute value of x minus 1 over natural log of 2 times 2 to the x minus 1/4 x to the 4th plus c. As a side note, it is sort of mathematical convention that this is a capital C, and math is a case-sensitive language, so you really do want to use capital C here as opposed to lowercase c. I know, it's right, like who cares, but the answer is math people care, and the person and or machine that is grading your thing is going to care, so it has to be a capital C, okay? But other than that, that's all there is to it. So term by term, right? So we had this overall big thing. We wanted an indefinite integral, so we want all of the antiderivatives, but we start by finding one. We did it term by term, and we just sort of reversed the derivative process for each. So that gave us the sort of function-y part of it, right? The antiderivative, and then we have that plus capital C, that plus C to give us all the other possibilities, okay? So that's that. Hello. So in this example, we are computing an indefinite integral, right? So we're going to start by finding an antiderivative, but the indefinite integral is all antiderivatives, right? So we're going to need to get all of them, so we need that plus c thing at the end. Nonetheless, we're going to tackle this sort of term by term, right? So start with the first part, so x squared. So we want an antiderivative for x squared. So that means that we want a function, right? We want to think of some function whose derivative is x squared, right? Again, if you sort of don't remember the core rules, we can sort of recover them in some sense, right? Thinking about what happens when you take a derivative of this kind of function. So this is sort of a polynomial thing, right? So if we take a derivative, it lowers the power by 1. So we can start by sort of increasing the power by 1 and see how close we are, right? So we can start by saying, okay, let's guess the antiderivative is 1 power higher, x cubed. We're going to take the derivative and see how close we get. Now, again, we don't really suspect that that's going to be the right answer, right? Because it's never that easy. But the hope is that we get close enough that we can sort of, adjust it a little and actually get something that's the right answer. So this, right, bring the power down, then subtract 1 from the power. So I'm going to get 3x squared, which is close. But we're off by that leading 3 because we want just x squared. But 3 is a constant, so my next sort of guess or my next sort of intuition would be to sort of get rid of that 3 preemptively by dividing by 3, right? And I can check. This is the nice thing about the integration process, right, about finding antiderivatives is, by definition, they're the thing whose derivative is what you're after. So you can always take the derivative and see if you are right. It's very easy to double check your work in that sense. Well, let me rephrase that. Very easy. It is straightforward. It may be computationally annoying, right? Like depending on how bad it is to take the derivative, that might be really unpleasant, but it is something that you at least theoretically know how to do, so you can do it. All right, so the 1/3 is a constant, so it sort of just pulls out. Then I multiply by 3, then I get that 3 minus 1. Those cancel, and I do indeed get x squared. So this thing, this x squared, this is going to be 1/3 x cubed. That's my antiderivative for that part. My next part is e to the x. And again, if we don't remember, right, e to the x being the super special function, but if we don't remember, we at least remember like it's an exponential, and exponentials have that sort of nice property that the derivative of the exponential is more or less itself, right? There's maybe some other piece that comes out of it. So we start with that. Again, not really expecting it to work, but expecting that, you know, maybe it'll show us where we need to go to make it work. But in this case, derivative of e to the x is e to the x. It actually just worked right out of the gate. So this is sort of the special case one, right? This is the one where the antiderivative is itself. There's nothing to be done there. Always nice to have to do nothing, right? And finally, we have this minus 4. So 4, I sort of think of as 4 times x to the 0, meaning that this is one of those, again, like the polynomial bit. So I can sort of increase the power by 1 and check. Now, maybe I jump ahead and be like, when I did this with the other polynomial, I had to divide by that power. So I'll divide by the power, although, well, the power is 1, so I'm dividing by 1 to do that, right? But, you know, whatever. So the 4 over 1 gets pulled out, so I have 4 over 1 times derivative of x, which is pulling down the 1, x1 minus 1. So this is just 4x to the 0, which is indeed what I want, right? This is just 4. So this tells me that, indeed, 4x is my antiderivative. So putting these things together then, my original problem, right, my indefinite integral, I have the 1/3 x cubed. I have the e to the x, right? So it's positive x squared plus e to the x minus the antiderivative of 4, which was 4x. So this gives me an antiderivative, but I want all antiderivatives, right? That's what the indefinite integral is. So plus c. Okay. And that is that. Okay.